once you record. Come on, record. Of course, the one time, right? All right, so we're going to move on from greenhouse effect to now how the winds are. So the wind section of this is going to encompass a lot. So we're on review book pages 131 to 132, but there's going to be add-ons to this. It's going to be how pressure affects the wind and so on and so forth. Okay, so here's the first slide. It says pressure differences, right? If you have high pressure, right? High pressure is when the molecules are going to be pushed closer together. That's when we have a cold system right here, right? So if it's high pressure, they're going to be lower to the ground. Versus when there's low pressure, right? The molecules are going to be further apart from each other and they're going to rise up. Okay, they're also going to be warmer. Okay, now, how does this work? Well, we have a high pressure system and a low pressure system. Okay, with a high pressure system, how do I know? Well, let's look, right? The outskirts, this should look just like the topographic maps we did, but now we're talking about isobars, right? Because we're doing this for pressure. And in the little blurb down here, it says circles are isobars with pressure in millibars. MB stands for millibars. Okay, so as we go towards the center, even if that H wasn't there, as we move towards the center, right, the numbers are increasing. So therefore, it's a high pressure system versus this side where the numbers are decreasing, which makes it a low pressure system. So it always moves, just like temperature, from high pressure to low pressure. So whenever you're watching the news, which you all were watching the last 2 days, hopefully because of the snowstorm that happened, right? They were talking about a high pressure system is moving in, which eventually led to the fun times that we had. So let's watch a little video. Hopefully it'll work.
Some people think the trade-in process feels too easy. They can't believe it's 100% online.
The word wind can mean many things. It can be peaceful, violent, powerful, exciting, bitingly cold, or searingly hot. Wind is everywhere, all the time. But where exactly does it come from? I mean, it's only air, which we've talked about a little before. But there are no fans or turbines or giant people in the sky blowing the air around. So where does the wind come from? Even when you don't feel the wind, the air is never totally still. If you zoom way in, you'd see air molecules bouncing around, colliding with each other and everything around them. So all that bumping and bashing creates a force. It's the force of all those bouncing air molecules over a given area of Earth that results in pressure. The air has mass, and gravity drives that air down towards the ground. That's why there's more air pressure down here than there is, say, on top of Mount Everest. The average atmospheric pressure on Earth is about 1 bar, or 100,000 pascals. But luckily, that pressure isn't pushing straight down. The force goes out in all directions, so we aren't squished into pancakes. Wind is what happens when air moves from high pressure to low. Anyone who's ever watched the weather knows that air pressure isn't the same everywhere, and that's because of temperature. Air near the equator is heated by the energy of the sun, so it becomes less dense and it rises. Near the poles, there's not as much heating by the sun, and that cold, dense air sinks down toward the Earth. Right along the equator, that creates this area with almost no wind called the doldrums. But wind doesn't come straight from the north or south. The Earth is turning, and because the atmosphere isn't attached to Earth, that causes the wind to curl and rotate. That's known as the Coriolis effect. If you want to experience that, just try to play catch on a merry-go-round. Pressure and temperature combine with a rotating Earth tilted on its axis and covered in sun-absorbing land masses. The winds of the Earth begin to swirl like a Van Gogh painting. So begins the swirling cycle of heating, cooling, and rotation that drives everything from gentle breezes to destructive hurricanes. Sometimes a little science can just blow you away. My name is Marie Curie, and I give It's Okay to Be Smart a glowing review. So subscribe. Ooh, I love the pinwheels.
All right, so like he was saying, right, it's always going to move from high pressure to low pressure, okay? And because of the fact that we are rotating at all times, right, you're going to create that Coriolis effect, which then gives us those rotating circles. Now, how exactly do they rotate? Well, let's look at a high pressure system first, right? The winds are at the center, right? And then they push outward, right? Well, how do they push outwards? In a clockwise fashion, okay? So it's going to be out and around, all right? What ends up happening is the air is actually going to sink down, okay? In other words, it sinks and moves away. Okay, so you have to memorize which ways that high pressure and low pressure systems actually move. Okay, so the fact that it's high, that means it's going to move outward and clockwise. Okay, we actually, during this time, you're going to have dry weather. Okay, looking at this picture from November 2003, look at the high pressure systems that are here. Those high pressure systems have no moisture around them versus the low pressure system over here has a ton, if it's green, it's usually rain, right? Has a ton of rain around it, okay? And you have all of these, it looks like topographic maps, but they're not. They're specifically for pressure, okay? So it's going to be high and dry. That's the kind of stuff you need to know, okay? So it's also known as an anticyclone, okay? I don't know why this came out like this. Let's slow this down a little bit, okay? It's an anticyclone. Why? Because when you think of a cyclone, you think of a tornado where at top it's really, really big and then it moves down into a small little thing. If it's the anticyclone, you want to think of a ball gown, right? On top, it ends up being smaller and then it goes out at the bottom. So for high pressure systems, they're the anticyclone, or you can call them a ball gown, all right? And how does it move? It moves clockwise and out, okay? For low pressure, it's the opposite. They're gonna move in, right? And if you think about it, it should make sense too, guys, because for high pressure, it goes from high pressure to low pressure. So if it wasn't going out, then it would never go towards the low pressure system. Whereas low pressure, it moves inward and up in a counterclockwise fashion. The two put together are the infinity symbol, if you think about it, okay? So in this case, the air is going to come together and rise up, right? And when you have a low pressure system, it's going to be wet, it's going to be stormy, it's going to have some sort of precipitation. And you're going to think of it as the L is like lousy weather. Okay, so it's L for low, L for lousy. Okay? Good? No? Yes? Maybe?
I need another second.
Okay. Thank you. Let me know when you guys are good. All right, so if you guys memorize either high or low, you just have to know the other one's the opposite. Okay?
I'm good.
Okay? So, low pressure systems are known as cyclones, okay? And the reason they're known as cyclones is because you have that uplift, okay? So they're coming in, they're going up, and at the top, they're branching out. Whereas the high pressure systems are going down and out. That's where they're diverging, okay? So if you can see them here, right? Here's just a picture of a hurricane, right? We have a hurricane symbol here. These symbols that you see around here with the little line with the feathers on them, those are called station models, and you will be using them to actually depict different things. You're also going to be using, or at least knowing what this front means, okay? When you guys are doing this, you're going to be using the reference table, specifically pages. We are at the bottom of page 13 in your reference table, okay? Right here, okay? If you guys have the review book, if you bought the review book, which is what I suggested you do, inside the review book, you have a reference table, so you won't ever have to print it out or lose it or whatever, okay? So, right, here we have lines all bunched together. So what is that going to tell me? That we have heavy winds. Just like we did for a topographic map, right? When we did this for the topographic maps, when the lines were closest together, we had the steepest slope. On an isobar map, when the lines are closest together, you're going to have the heaviest winds. When they are furthest apart, they are going to have the lightest winds. So yesterday during the storm, if you were to print it out and actually see where the pressure changes were, they were going to be super close together because you could tell that we had a ton of wind yesterday. All right, so how do we draw winds around a high and low pressure system? Just like I did before, right? Around a high pressure system, it's going to be clockwise and out towards the low pressure system, which is going to be counterclockwise and in. And if you look at them, they kind of look like the infinity symbol, okay? But it starts at the high pressure and goes to the low pressure, and then it goes in and up from there. Okay, so for high pressure, it's going down in a counterclockwise fashion, and then it goes out, whereas on the low pressure, it's going in and up. Okay? All right, so let's do some practice questions. Question number 1. The arrows show the wind direction. Is this going to be high pressure or low pressure?
Low,
Why?
because it's going inward.
It's going inward. Anyone agree or disagree?
I agree.
Agree.
I agree.
Good. All right, so it's a low pressure system. So if it's low, is it going to be moist or dry air? Is it going to be wet or dry?
Wet.
Moist.
Very good. Okay. I love how I like random. I don't even know how that happened. All right, so which direction do the winds curve in the northern hemisphere? This goes back to everybody's favorite reference table. Which directions is the winds going to curve in the northern hemisphere? Are we talking clockwise or counterclockwise? Which way are we going?
Is it clockwise?
Why?
Because of I forgot what it was called, but I don't remember.
Anybody remember why? Goes to the right, right? Why? Because of the Coriolis effect and how we rotate. Okay, so it depending on which way. So you can't really say clockwise or counterclockwise because it depends on which way you're facing. It's always going to be, if you're in the northern hemisphere, it's always going to be to your right. Okay. And that's everybody's favorite reference table. You guys remember me talking about it? It is this one. Right? Everybody's favorite reference table. Yeah. Right? In the northern hemisphere, goes to the right. In the southern hemisphere, it goes to the left. Right? It all comes back to Earth's rotation. and the Coriolis effect. You guys, this is a review. Remember I said everything in earth science comes back? This is one of them. It's not like you're just forgetting what you learned from first and second quarter. It builds on it, but it doesn't seem like it until now. Okay? So, is this clockwise or counterclockwise?
Clockwise.
Clockwise.
No, clockwise. Clockwise.
Okay. All right. So, does that mean this is high pressure or low pressure?
High pressure.
High pressure.
Good. Right? Good. So you're going to have to be able to look at values like this and say, without the H there or without the L there, is this a high pressure system or a low pressure system? And with a high pressure system, do we have moist or dry?
Dry.
Very good. Woohoo. Okay, so we're going to move on to sea breezes. All right. The thing with the sea breeze, right, we kind of started talking about this when we were talking about specific heat, right? When the land heats up, right, and the air above the land heats up, it's going to make the molecules move more. So during the day, when the land is absorbing the heat, you're going to get a nice sea breeze that comes in. Why? Right? Because we talked about specific heat. Right? The land is going to heat up faster because of that lower specific heat. That one lab that we did comes back so much during weather. Okay? So that specific heat capacity lab that we did that most of your friends in earth science did not do makes this so much easier for you because you saw it happening. All right? You saw how the land was heating up faster because it has a lower specific heat. Right? So the molecules that are over here in the air are going to warm up, right? When they warm up, they move further apart. When they move further apart, they become less dense and they increase, right? They go up, right? Well, then what's going to happen? A convection current happens, right? From the heating source, which is here, it moves up, it moves away from the heat source. And then since it moves away from the heat source, those molecules start to cool down and they start to move slower, so they become closer together and more dense, which makes them sink down, and then back to the heating source we go. So for a sea breeze, if it says the word sea in front of it or ocean in front of it, the cool, more dense air is coming off of the ocean towards the warm land. So whatever it says in front of it, sea or ocean, that's going to be the cooler side, okay? Right, so this is just showing you. Now, notice the difference between this picture and this picture. The water just happens to be to your left in this picture. In this one, it happens to be on your right. So you have to be careful, just like we did with the apparent motion graphs, which way was north, right? Which way is the water? If you want to take a picture of this, you can. I will give you a second. Okay, so, and this actually I like better than the first picture because it explains how the cool air sinks back to the surface, goes towards the land by the wind, the land heats it up, and it goes up, and then it moves away, and then it goes down. And it also has where the high and low pressure systems would be. Okay, whereas a land breeze only occurs during the night because during the day we have that heat source which is heating the land, right? Whereas during the night, we don't. But the ocean is still warmer at night than the land, right? Why? Because water has a higher specific heat, which means that it's going to take longer to heat up and cool down. So all night long, the water is giving off that excess heat that it absorbed during the day, whereas the land is already cool. So here's the same picture, but now it's nighttime, right? Your heat source is going to be your water because it has that lower specific heat, right? And it's releasing heat slower, right? So it will warm up the molecules over the water, which makes them move further apart, which makes them less dense, and rise up, move across, cool down over the land and then back. So like I was saying before, whatever it says in front of the word breeze, that's where the cool air is coming from. Okay, so for a sea or ocean breeze, that's where the high pressure system and the cooler air will be coming from. Whereas if it's a land breeze, that's where the high pressure and cooler air is coming from. Okay? So here's just another picture showing it. Okay? And again, this time the water is on our right, whereas in the last picture, the water was on our left. Okay? Just a little bit of a review here, right? We know we have contour lines, isobars, which was for pressure. Now we have isotherms, right? We've talked about all of this, so this should be a review for you. We talked about it when we did topographic maps, okay? Variations in temperature, it just means that it's going to change from the average value. So we've had a cooler temperature yesterday, right? So it's going to be a variation. So one of the factors for these variations is latitude. Locations that are north of the equator are going to experience cooler temperatures. And as the latitude increases, that means you're getting closer and closer to the North Pole, right? It's going to get colder and colder. Right? This should be a review for you because we've already talked about this, right? So here we have just a picture of, right, closer to the equator down here in Florida and the bottom of Texas. And as we go north, it's going to get colder, right? Another factor, we talked about this as well. If you were more inland versus a coastal city, right? You know that cities that are by the water are going to experience cooler summers because you have that breeze coming off the water and it's going to regulate the temperature, right? And elevation is the third one, right? As altitude increases, we know the temperature decreases, which is why at the top of Mount Everest, there is a ton of snow because you're at a very, 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 very high altitude. Okay?
Ms. Gonzalez?
And that is the end of the period, guys. So once you get this, you can go. I'm just going to really quickly stop recording. Where are you? Oh, where'd you guys go? Okay, I'll put it back up in a second so you can finish.